Okay, now let's continue with the ground canonical systems. That's what we call them. Particle systems that exchange particles and energy exchange. With a particle and heat reservoir. So you can imagine your system as a subsystem interacting with a heat band. But now the separator is allowed to the passage of particles, okay? Depending on the chemical potential, reservoir, your system of interest. Let's imagine we are specifically interested in a state where the energy is E and number of particles is N in your system. Total energy is E total, and number of particles is total number of particles N of T. So the total number of microstates available to these interacting systems will be written as the multiplication of individual number of microstates available to each. And that's our probability that will be proportional to that number. So the probability of finding our system with energy E and number of particles N is going to be proportional to, since that is a single state we are interested in, we are trying to find our system, subsystem, with energy E, a number of particles in it, N. So it is a specific microstate. We have one of them, okay? Yeah, I have some competition, I know. But I think you can hear me. Huh? That is going to be proportional to number of microstates available to the heat and particle reservoir. And of course, when I exponentiate, you'll see this is proportional to e to the entropy. The reservoir. So if I Taylor expand, I'm going to be a little bit sloppy just to show you what you have seen in your undergraduate lectures. Well, here's the entropy. Taylor expanded. being sloppy means I'm not specifying what I'm keeping constant. You should do a better job at this. But that is the general expression. And of course, this is 1 over temperature, absolute temperature. That's del S del N is minus mu over T. Now, of course, chemical potential shows itself, because that will be the quantity that will decide on the particle exchange or directional particle exchange from your system to the bath or from bath to your system. Usually the second case. So this side becomes S for the total energy and total number of particles minus E over T plus mu N over T. So that the probability is proportional to that exponential, leaving aside the constant term. Probability of finding our system with energy E and number of particles in it to be equal to N. I have to specify these quantities, of course. It's proportional to exponential minus E minus mu N over KBT. Have you seen this factor before? Yes, of course. This is known as Gibbs factor. The first one earlier on was what? Boltzmann factor. This is Gibbs factor. Or Gibbs distribution function, or grand canonical distribution function. Because these systems are called grand canonical systems. Well, let's formulate this in this way. When you have a system held at constant temperature T at equilibrium, isn't it? That's the condition for equilibrium. And at constant chemical potential mu, that's also needed for equilibrium. The particle exchange will go till the chemical potentials are the same. So for your system at constant temperature and chemical potential, this is the probability of finding your system with energy E and number of particles in it equal to N. Okay? That's the exact state. So, if you want, let's repeat again. If you want to normalize, we have to specify how many energy states we have, how many possibilities for the number of particles for our system in the following form. Let's do that for the grand canonical case. If we specify the possible different energy values and possible different number of particles for our system, we have to write this probability as PRS. It was PR only for the canonical case, which is proportional to exponential this exponential minus alpha NR, well, let's call this NS minus beta ER. Keep R for E, but it doesn't really matter. Just to make a contact with the canonical case, isn't it? I wrote it as ER in that case. So the probability of finding our system with energy ER and number of particles in it, NS, is proportional to this Gibbs factor. Is that okay? Here, of course, alpha is minus mu over kBt, and beta is 1 over kBt, isn't it? Huh? So I have defined another constant, let's say, proportional to chemical potential. But physicists are lazy sometimes not to rewrite every time 1 over kBt. We say beta and alpha, and that's it. Okay. Now, let's normalize, as we did for the canonical case. If we normalize this, the normalized probability is, well, exponential minus alpha NS minus beta ER. But in your book, it may be the other way around. It doesn't matter, isn't it? NR, ES, it doesn't make any difference because these are dummy variables. You are just summing over them. Divided by the sum over all states that's the normalized probability. If you sum these probabilities, you will get 1, isn't it? The sum in the numerator will be equal to the sum in the denominator, so divide them, you get 1. It is properly normalized. Now here we have a sum. What was the sum in the canonical case? It was a simpler sum, isn't it? The sum in the canonical case, now I will concentrate on these sums because they are very important in statistical mechanics. They have a special name. Do you remember that? You don't remember anything. We have discovered that for the canonical case, systems, the sum was, let's call that sum Q. What was it? Well, it was function of NBT, and the sum was over all states with energy ER over kBt, isn't it? Or simply e to the minus beta ER. Here the temperature was constant at equilibrium, the same temperature with the heat bath. Okay, the sum is over all microstates with energies E sub R. That sum has a special name, just like that sum. It is the partition function of the system. Partition function. Now you remember. It's called partition function. This is canonical partition function. This is grand canonical partition function. Let's give it a name. Well, usually this is also called Z. That quantity is a little bit more complicated. It's called curly Z or curly Q. How am I going to write curly Q? I don't know, but let me try. Equal to something like this. This Q is not the same as that Q. This is grand canonical, or curly Z. Grand canonical partition function, canonical partition function. See how easy I got it from very easy considerations? Probably you have done this in your undergraduate statistical thermodynamics course, and I'm sure you did that. Now, why are we giving them special names? Because you can get the whole thermodynamics from these functions. They are so powerful, they give you the whole thermodynamics. Let me show you one. In the canonical case, for example, then what is the average energy? Let's look at the canonical case. Let's write the average energy. Well, average energy is also known as internal energy in canonical systems. Sometimes we call it U. And that energy is nothing but probabilities multiplied by the energies, corresponding energies, sum overall system. What is this? Let's try to show why the partition function is so important, okay, for our calculations. This sum, well, when you look at it, is what? ER e to the minus beta ER, isn't it? Divided by Q, huh? Well, when you look at this, you can relate that to our partition function Q. It is nothing but, well, it is like taking derivative with respect to beta will bring down this factor, isn't it? So this is nothing but minus derivative with respect to beta of logarithm of Qn Bt. Sometimes we write the canonical partition function like this. Okay, that is Q for number is fixed here. That's why we call it Q sub n, V, and T. Isn't it? How do you take derivative of logarithm? 1 over the function, derivative of the function. Is that clear? Now, here's your internal energy from partition function. So extremely important. It's something that you have to know well in statistical mechanics, how to get this from very simple expressions that by doing over and over again the same calculation, you will remember these relationships. But when the course is over, you don't remember anything. That is surprising. And one very important aspect of statistical mechanics, it brings together very many different areas of physics, like electromagnetic theory, quantum mechanics, classical mechanics, everything now comes together. Usually you think that these courses are not related, but to understand any physical phenomena, you need all of them together. That's why in your mind, in your studies, you have to bring them together. Never forget one. At least the most important things, okay? Do you have any questions with this? Now you remember everything. Let's have an application. Let's apply this to an ideal gas, classical ideal gas. Let's see what we get when we apply this much of knowledge to an ideal gas. Are we going to be able to get everything about the gas? Thermodynamic properties of that gas. Okay, here is the example. The examples I'm going to give is like, well, the set of examples is like a set of problems, if you like, isn't it? To apply something to a physical problem. Now, one important difference between thermodynamics and statistical mechanics will be very clear, and it is discussed in your book. Please read that related chapter. Classical thermodynamics, or thermodynamics in general, depends on experimental observation and generalizations, isn't it? There are 4 laws of thermodynamics. We can recall them. 4 laws. And the findings of thermodynamics, when you apply it to systems, are quite general, isn't it? Very general. But statistical mechanics is not. It is model dependent. It depends on the model you are using. Okay? Here we are going to use a model of an ideal gas. A gas with no interactions between particles. That's what we mean by ideal. Let's do that case as an example. Or you can look at it as a problem-solving session. By the way, we are going to have problem-solving sessions with the assistant to the course. Do you know him? Ismail Cem Lider. So he's going to have some recitation hours with you. You usually ask for it when the exam is closed, but don't do that. Do it quite often. Make him work a little bit to earn his money. Okay, let's apply the things that we have learned up to now to an ideal gas. If the particles are not interacting, we can say surely that there are no spatial correlations. That means the presence of one particle doesn't influence the presence of other particles, isn't it? If a volume V available to one particle, the same volume will be available to another particle. There is no correlation between positions. The particle doesn't feel the presence of others. No interactions between them. If there are interactions, it's not the case, of course. As we are going to see when we deal with interactions, then the presence of one will influence the presence of others. So that's the meaning of no spatial. In space, there is no correlation between positions of particles. Okay? No correlations among particles, non-interacting. Total number of ways n particles will be distributed. That's what we are looking for, omega, isn't it? Total number of ways n particles can be distributed in a volume V, in a box with volume V. Well, this is, of course, the product of a number of ways individual particles can be accommodated on the same volume. Okay? Number of ways individual particles can be accommodated in the same volume. Huh? Well, this number of ways one particle to be accommodated in volume V is proportional to V, isn't it? Bigger the volume, bigger the number of ways. So this is nothing but multiplication of all the volumes. So this number then is proportional to V to the n. We have n particles, each one having V. V times V times V up to n is V to the n, isn't it? So, if that is the case, we can get our entropy, Kb ln omega, well, it is proportional to Kb ln or n ln V plus a constant, ln C, for example. And by taking derivatives, we can get the pressure, del S del V, and E. How clever, isn't it? Now we can get the pressure if we know number of particles and volume. It comes out to be, when you take the derivative with respect to V, it is 1 over the V, nothing else. So NKB times 1 over V. That was expected, isn't it? Well, this is nothing but PV equals NKBT. This is ideal gas law, or equation of state for an ideal gas. How easy to get, isn't it? In thermodynamics, you get to this relationship by doing experiments, observations about systems. Now, you should be careful in counting states, okay? If you think about this counting as normal and correct, you may run into problems. And your book has a very nice example for this. Let me mention that problem. Here you can get exact value of S for an ideal gas, isn't it? If you do the calculation correctly. And it is done in your book. Since I have a very limited time, let me give you the result and refer you to the book for the entropy. And I will underline a problem with it. There's no problem with that, of course. It is coming out very clearly. That's correct. But if you want to calculate entropy, and I will do it later, I will drive it later. Entropy comes as function of NV and energy E, NKB logarithm V over H cubed 4 pi ME over 3n to the power 3f plus 3f NKB. You should always find entropy in terms of NKB. That's the correct unit. Now, if you look at this, you can use it for many purposes. One purpose is to get the energy, average energy of your system, ideal gas, isn't it? What do you expect for your energy for the gas? We don't know. Well, invert to get energy. How are you going to invert this? Well, take exponentiate both sides, isn't it? That's the way to invert it. If you exponentiate this, you get energy as function of entropy, volume and number of particles, 3h squared n 4 pi m v 2/3 exponential 2s divided by 3nkb minus 1. That leaves the logarithm alone, so you can exponentiate. Now, let me go from here to temperature. It was derivative with respect to E, keeping N and V constant. It's very easy to take derivative of S with respect to E. keeping everything else constant. It is an exponential relationship. The result is three NKB over 2E. Do that. That gives you the energy, total energy. It is that energy is 3 over 2 NKBT. Is that what you expected? Why? Because you know something from classical mechanics, which is called equipartition of energy, and it says each degrees of freedom contributes 1/2 kBT to the total energy. You have 3 degrees of freedom per particle, 3 times 3 over 1/2 kBT times the number of particles. That's the total energy. That's correct. It is wonderful to get that, isn't it? Very easily done. QED. QED. Can you calculate? Okay, let me give you the first homework then. Can you show, I'm not going to collect these, I'm going to give you problems as homeworks, but not these. These are just to make you, huh? Huh? To get this, of course, temperature. The CV, del E del T, keeping V constant, well, 3 over 2 NKB, isn't it? T, NKB. There's no. Why don't you calculate this? Now you have to use enthalpy. The same thing with enthalpy. You have to keep pressure constant. Can you show that this is 5 over 2 NKB? Show that. Huh? It's a very simple calculation, but it warms you up to the subject. You start doing things with your hands. So that gamma, which is Cp over Cv, comes out to be 5 over 3. Okay? So, gamma. There's very nice passages in your book about change in entropy during an isothermal process, a diabatic process, whatever. You should be familiar with this. But here there's a problem. Can you tell me the problem by looking at your expression for entropy? I gave you an expression for entropy. Look at it. Can you find a problem? There's a problem. This one. Huh? You might know that. Well, the problem becomes clear when you consider entropy of mixing. It leads to Gibbs paradox. You have to read about it, another homework. Gibbs paradox. The reason is that this is not extensive. So there must be an n in that expression. You have to divide that v by n. If you don't have that, you have a problem in studying entropy of mixing of two gases together. Why don't you look into that problem? Huh? Since we are interacting always, I want you to come ready for the next lecture by looking into this problem. Okay? That is a nice habit. You should read before coming to class. So I give you a problem to read about and come to the next lecture already ready. Do you have any questions up to now? Anything that you want to ask? If not, I think you deserve your lunch now after 3 hours of lecturing, listening to lecture. Thank you very much.